Good morning everyone. In today's video tutorial, I'm going to explain how to find the magnitude spectrum of a PPG signal using DFT and then compute the pulse rate using this DFT. And then again we'll be comparing the pulse rate that we obtained through DFT and the one pulse rate we obtained through autocorrelation in the previous experiment. So let's get started. So what exactly is DFT? DFT stands for discrete Fourier transform. It converts a finite sequence of equally spaced samples of function into a same-length sequence of equally spaced samples of the discrete time Fourier transform, which is actually a complex value function of frequency. The interval at which the DTFT is sampled is the reciprocal of the duration of the input sequence. The DFT is said to be a frequency domain representation of the original input sequence. If the original sequence spans all the non-zero values of a function, its DFT is continuous and periodic, and the DFT provides discrete samples of one cycle. If the original sequence is one cycle of a periodic function, then the DFT provides all the non-zero values of one DTFT cycle. So this is exactly how the DFT works. The mathematical expression for calculating the individual frequency component of a signal in DFT is as follows. So capital X of k is equals to summation small n is equal to 0 to capital N minus 1 x of small n e to the power minus 2 pi I k by capital N for all k belonging to 0 to capital N minus 1. Here x of n is our input sequence. Again, the inverse discrete Fourier transform is computed. Inverse discrete Fourier transform is computed as follows, where input sample is obtained as summation k is 0 to capital N minus 1 into x of k e to the power 2 pi I k n by capital N whole divided by n for all n belong to 0 to n minus 1. This is how the DFT matrix would look with all these values at 1 and these values, as you can see, with n minus 1 n and extending up to final value of n minus 1 n minus 1 and n. So let's see how to calculate the DFT for the PPG signal. This is the implementation of this experiment on the Arduino Duo board. Here this is the input sample. Now to find the DFT matrix, we have divided the matrix into two parts, that is the cos matrix and the sine matrix, and then we find the real and imaginary parts to finally find out the magnitude response. So this will be the cos matrix and this will be the sine matrix, and this is the real and imaginary parts of the output. Here we have initiated the value of pi to 3.14. This loop actually shows how we can get the cos and the sine matrices. Here the sample size is 75. Now in this matrix we actually get the real and imaginary part of the matrix. So here the two parts of the matrix, the two matrices are formed, and to finally find the magnitude response we find the square root of the real part and the imaginary part. This part was for the printing of the magnitude function, and here we actually find out the pulse rate, where the pulse rate is defined by the peak value and then position of the peak value, and in printing this position with certain values, certain constants, multiplying these values with certain constant would give us the pulse rate, where this this here is the position value of the peak, this is the sampling rate, and this is the number of samples. So this is the plot we obtain after the after applying the DFT matrix to the PPG signal, where this is actually one plot. This part from here to here is one part. So you can see it basically has two different peaks. So we will be taking the first peak for our calculations. As you can see, the pulse rate that you obtain using this one is 60. That means we obtained the peak at somewhere around 3. But similarly, in the last experiment, we used the similar sample and same sample, and the pulse rate that we obtained through correlation was 71.43. You can see there is an error percentage of 19.05, which is quite high. Now we will be implementing both autocorrelation and DFT on the PPG signal in MATLAB. So here is the data input. This is the sampling frequency. Now to find the DFT and the DFT matrix, this is the code. And here we find the pulse rate of the PPG signal using DFT method. Now here we are implementing the autocorrelation function. These are the basic commands that are used in MATLAB for finding autocorrelation. Here we find the zero crossing to find the pulse rate later. At the end, this is the pulse rate that we will be obtaining using autocorrelation. The autocorrelation plot in MATLAB for the PPG signal that we had looks something like this, which is similar to the plot we obtained in the previous experiment. Same goes for this plot of the DFT for PPG signal. This is also similar to the one plot I showed you earlier in this video. Now to tell you that the pulse rates that we obtained through MATLAB is the same as the pulse rate we obtained through DFT and autocorrelation when implemented on the Arduino board. So in this experiment, we have actually understood how to find the frequency of the signal and ultimately the pulse rate of the PPG signal using DFT method. We have concluded that upon using signals with low sampling rate, as with 75 Hz in our case, the resultant pulse rate is worse than what is obtained using the autocorrelation method. I'm sorry, this will be low. This is 25 Hz, not 75 Hz in our case, and the resultant pulse rate is therefore quite worse than on the autocorrelation method. So with this, we come to an end in this video tutorial. Thank you.